Welcome to the Zodiac Digest channel, my dear friends. Lightning. What is it? How is lightning born? Why does it happen? What types of lightning exist? St. Elmo's fire. How dangerous is lightning and can it be controlled? Friends, don't forget to subscribe and leave your comments. Let's go. Electricity in clouds. How do they become charged? This is one of the most complex questions in the physics of lightning. If we're talking about regular lightning that occurs in the clouds above our heads, many processes take place within them. In different phases, clouds contain water droplets, hailstones, ice crystals, and even supercooled water particles. Thunderclouds are characterized by strong turbulence and powerful air currents that move in circles, collide, break apart, and rub against each other. As a result of these processes, particles become charged. It's important to understand where clouds get the energy for turbulence. The answer lies in the process of condensation. On hot days or during significant temperature changes, an ordinary cloud begins to rise and expand. As it does so, it cools, and water droplets condense, releasing heat. This heat fuels the cloud's upward movement, enhancing the Archimedean force. The higher the cloud rises, the more it expands, and the condensation process continues especially intensely in areas where the temperature approaches zero. Inside the cloud, a complex turbulent process occurs with vortices of various scales, from small to large. This entire system moves at tremendous speeds, sometimes reaching 43 meters per second. Particles inside the cloud rub against each other, collide, and break apart. Lighter particles are often positively charged and rise to the top, while heavier, negatively charged particles remain at the bottom. This leads to charge separation. Reference books state that the charge difference inside a cloud can reach up to 3,000 volts per centimeter. Considering that clouds can be a kilometer in diameter, the potential difference within them can be on the order of 1 billion volts. On average, the potential of lightning is estimated to be hundreds of megavolts, making this phenomenon truly grand. The difficulty in measuring the potential inside a cloud lies in the challenge of access. Nevertheless, lightning potentials range from hundreds to thousands of megavolts. This is why lightning remains such a bright and impressive natural phenomenon. Most often, lightning occurs within clouds or between clouds. This is because discharges within clouds find a shorter path to release. For example, in mid-latitudes, lightning forms at altitudes of 4, 5 kilometers and sometimes even higher. To reach the ground, a discharge requires more time. This is why discharges within clouds occur 10 times more frequently. A discharge originating from a cloud can initiate other discharges. These, in turn, become more powerful and are directed toward tall structures. Why do lightning strikes often hit temples and churches? Lightning has captured human attention throughout history. It often struck temples and churches, which were the tallest buildings on elevated ground. These structures, made of conductive materials, seem to attract lightning. The height and location of a temple increase the likelihood of a strike. Because of this, people in the past perceived lightning as a divine act. Is lightning a random process? There is a theory that lightning is triggered by cosmic particles, which help form ionized paths for discharge. However, lightning remains a random process. Its trajectory and point of impact depend on many factors, including atmospheric structure and the presence of tall objects. Tall structures not only attract lightning, but can also generate it. For example, near an observed TV tower, up to 30 lightning strikes can be recorded in a year. An approaching lightning strike draws charges from nearby objects. Tall buildings meet lightning with their upward charges, and when they collide, the discharge reaches the ground, causing destruction. Do lightning strikes move toward each other? Yes, lightning can indeed move toward each other. When a discharge approaches the ground, it draws charges from tall structures. Upward channels strive to meet the descending discharge. Once this happens, a current flows through the channel, reaching tens or even hundreds of kiloamperes. This is the primary mechanism of destruction during a lightning strike. How long does lightning last? Lightning is a phenomenon that impresses with its power, but lasts for an extremely short time. On average, a lightning flash lasts about 0.2 seconds, though it can sometimes extend to 1 or even 2 seconds. However, lightning consists of multiple strokes that occur within a single flash. After the first stroke, which we see with our eyes, another follows within 30, 60 milliseconds. This is why lightning sometimes appears to flicker. In reality, it's not a single discharge, but a sequence of strokes. In mid-latitudes, there can be dozens of such strokes, and the lightning can last more than a second. All these strokes travel along the same channel, which has already been prepared. This channel is made of plasma, ionized, charged gas, that allows subsequent discharges to pass through it. Between strokes, the plasma partially dissipates, but then reforms. This is why lightning can strike the same spot multiple times, often up to 4 times in a single flash, and sometimes even more. The energy released by lightning is astounding. A single discharge can melt sand, turning it into glass. The charges accumulated in clouds can reach values of 30, 50 coulombs. Considering the potential, measured in billions of volts, the energy of a single lightning strike is on the order of 1 billion joules, and sometimes even reaches 10 billion joules. The main reason for lightning's destructive power lies in its enormous currents. They can reach tens of thousands of amperes. For example, a lightning strike can carry 30, 50,000 amperes, and although the strike itself lasts only fractions of a second, the energy released can cause significant damage. Lightning is not just an earthly phenomenon. It has also been detected on other planets, such as Venus. With its hot surface, powerful convection, and massive clouds, Venus seems like the perfect environment for lightning. It has even been called the planet of storms. However, the question of lightning on Venus remains controversial. The first Soviet spacecraft that flew past Venus carried lightning detectors, which recorded discharges. Later, American satellites passing by Venus failed to confirm these observations. Thus, the question of whether lightning exists on Venus remains open and requires further study. Lightning and thunderclouds seems impossible without the involvement of cosmic rays. And we're not just talking about ordinary cosmic rays, but galactic and extragalactic rays with extremely high energy. Any discharge, including lightning, is a process of electron multiplication in an electric field. However, even powerful electric fields cannot pull electrons out of atoms or molecules. To start a discharge, a first electron is needed. Near the Earth's surface, such electrons are generated 80% of the time by the decay of radioactive radon gas, while the remaining 20% come from cosmic rays. But at altitudes of around 5 kilometers, where radon is almost absent, cosmic rays play the primary role in generating the first electrons. They initiate the process that leads to the formation of lightning in clouds. Modern research shows that lightning is not born from a single electron, but as a collective phenomenon. This requires energetic particles distributed over hundreds of meters within the cloud. These particles form what are known as extensive air showers. When a fast, energetic proton from space collides with molecules in the atmosphere, it triggers the multiplication of secondary particles. These particles, moving in the same direction, create a kind of shower. If such a shower enters a thundercloud with a potential of hundreds of megavolts, the particles gain additional energy and contribute to the birth of lightning. Meteors passing through the atmosphere leave behind glowing plasma trails. These have no connection to lightning. Meteors burn up in the upper layers of the atmosphere at mesospheric altitudes, around 50, 60 kilometers. They do not reach areas with sufficient electric fields to produce lightning. Therefore, lightning does not strike these trails. St. Elmo's fire. What is it? St. Elmo's fire is a long-lasting corona discharge accompanied by a crackling sound. This phenomenon has inspired many myths and legends throughout history. It occurs during a thunderstorm or as one approaches. This discharge is observed on sharp, high conductive surfaces, such as ship masts, especially in conditions of high humidity and salty environments. A poet once described this phenomenon in his verses, "On the night before the storm, the masts are lit with St. Elmo's fire." It occurs during a thunderstorm or as one approaches. This discharge is observed on sharp, high, conductive surfaces, such as ship masts, especially in conditions of high humidity and salty environments. A poet once described this phenomenon in his verses, "On the night before the storm, the masts are lit with St. Elmo's fire." St. Elmo's fire forms when charged thunderclouds create strong electric fields. For example, negative charges dominate the lower parts of the clouds, causing tension on the surfaces of objects like masts or tall buildings. However, the energy is insufficient to form a full-fledged lightning strike, so faint glowing discharges appear instead. During rain, a corona discharge occurs on high-voltage wires, creating a characteristic crackling sound. This is the result of electric fields acting in high humidity conditions. The crackling can even be heard in the radio frequency range. Corona discharge is used in cosmetology for skin treatment. There are devices that use low-power electric discharges to help address skin issues, such as acne. This process resembles the action of a stun gun, but is much less intense. The currents are small, and their effect feels like a light tingling sensation that stimulates the skin. Lightning strikes land more frequently. This is because land heats up and cools down faster than water, creating conditions for more intense convection. However, over warm seas like the Mediterranean, thunderstorms are also common, especially in winter when cold air from the North Atlantic collides with warm air masses over the sea. In Israel, for example, summer thunderstorms are rare, while winter storms are accompanied by heavy rains and thunder. This is due to instability. Warm air rises, cold air sinks, creating turbulence that triggers thunderstorms. How often do lightning strikes hit ships? Ships, especially large ones, are often struck by lightning because on the smooth surface of the water, they act as tall, conductive objects. To protect against lightning, ships are equipped with lightning protection systems. This includes metal rods that divert the lightning current through conductors to a grounding plate beneath the hull. If the lightning protection is poorly implemented, a lightning strike can cause serious damage, injuries to the crew, or even fires. Modern ships are equipped with special cables and systems that intercept discharges before they can cause harm. Aircraft frequently encounter lightning because they fly at altitudes where thunderclouds and cumulonimbus clouds, rich in electric charges, are located. On average, a commercial aircraft flying about 3,000 hours per year is likely to experience at least one lightning strike during that time. A lightning strike on an aircraft is often initiated by the aircraft itself. As a large metal object, it polarizes the surrounding electric field and can create conditions for lightning formation. Such strikes are usually safe because aircraft are equipped with lightning protection systems that channel the charge through special conductors. Electric fields in clouds and interactions with streamers, small discharges, facilitate the current within lightning. These streamers charge up and expand, allowing lightning to travel at speeds of up to 100,000 kilometers per second. This speed is impressive, though significantly slower than the speed of light. Ball lightning, fact or myth? Ball lightning is a real physical phenomenon, not an optical illusion. Research based on eyewitness accounts and video recordings confirms its existence. Moreover, reliable video footage has been captured, accidentally recording ball lightning while observing regular lightning. Previously, it was believed that ball lightning could be an optical effect caused by retinal fatigue. For example, the bright flash of lightning could leave an afterimage on the retina, similar to the effect of a strobe light. However, modern research shows that ball lightning is a physical object, not a trick of light. The main mystery of ball lightning lies in its longevity. It can exist for several seconds or even longer, making it unusual compared to regular lightning. Some scientists believe that ball lightning can be reproduced in a laboratory using electric discharges or microwave energy, creating spherical forms. However, the nature of its longevity remains a subject of further study. Why does ball lightning last so long? Ball lightning is a rare phenomenon capable of existing for dozens of seconds. Many witnesses, including scientists, have observed it, and some have even conducted chemical analyses of the traces left behind by ball lightning. For example, one scientist collected an air sample from the tail of ball lightning and found products typical of discharges, such as nitrogen oxides. The main question is why ball lightning lasts so long. Regular lightning exists for a very short time because all its energy is quickly discharged. The plasma-forming lightning is unstable. Positive and negative charges tend to recombine, causing the plasma to dissipate. It is believed that for ball lightning to exist for an extended period, a constant energy source is required. For instance, in laboratory conditions, an electric discharge can be sustained by supplying energy, as in the case of a voltaic arc. However, natural ball lightning hovers in the air without any visible energy source, which remains one of its greatest mysteries. Ball lightning is often observed during thunderstorms or immediately after a lightning strike. It can move, pass through narrow gaps, and even enter through windows. Unlike regular lightning, it lacks a conductive channel, making it an even more unusual phenomenon. The mechanism supplying energy to ball lightning continues to inspire numerous theories, including suggestions of nuclear processes or other complex physical mechanisms. Lightning that flies into space. Lightning directed into space is a rare phenomenon associated with unusual atmospheric processes. In 1989, a phenomenon called Sprites was discovered. These are giant discharges that occur at altitudes of 50-60 kilometers and spread both upward and downward. They can reach kilometers in width and tens of kilometers in height. Sprites were accidentally recorded by one of the researchers who was observing clouds from a high vantage point. He noticed discharges above the clouds and later confirmed them using a camera. These discharges were published in a scientific journal, but initially many scientists were skeptical. Only after analyzing old space footage did it become clear that such discharges indeed exist, though they had previously gone unnoticed. The physics of Sprites is explained as the result of an electric field remaining after a regular lightning strike. Such a field can be strong enough at high altitudes to form a discharge. Sprites are, in a way, the children of lightning, and their study continues, helping us better understand electrical processes in the atmosphere. Elves. Electromagnetic waves. When lightning strikes, it creates a powerful electromagnetic wave that propagates from the strike site in the form of a donut at altitudes of about 100 kilometers. These waves are well detected from space, for example, by satellites and specialized instruments equipped with highly sensitive sensors. This process occurs synchronously with the lightning strike. After the strike, the electromagnetic wave begins to propagate. Scientists record it as a flash on the cloud, followed by the expansion of the electromagnetic field. Such waves created by lightning are known as Elves. These are electromagnetic waves so powerful that at altitudes of about 100 kilometers, they can generate discharges. Jets, giant discharges from clouds. Jets are giant discharges that occur at the upper boundary of clouds. They can reach heights of 9,100 kilometers, extending to the lower part of the ionosphere. Jets do not form clear channels, but instead expand and become diffuse, spreading through the space between clouds and the ionosphere. Atomic explosions and thunderstorm activity. In the 1960s, atomic and thermonuclear tests were conducted in the upper atmosphere and even in space. These explosions stimulated thunderstorm activity. During these tests, lightning and discharges were observed and photographed by scientists. The explosion creates a powerful energy flow that, like a volcanic eruption, causes friction and discharges similar to lightning. However, data on the impact of these explosions on overall thunderstorm activity remain limited, as systems for meteorological detection of lightning were not well developed at the time. Radio receivers and lightning. Radio receivers can detect electromagnetic pulses generated by lightning. These act as a kind of lightning detector. The most powerful signals are recorded in the kilohertz range when lightning strikes the ground or when lightning channels meet in clouds. Additionally, streamers, which facilitate the movement of lightning, create radio signals in the megahertz range, 3,300 megahertz. Why are lightning still a mystery? Despite progress in studying lightning, their origin in clouds remains an open question. For example, to create a discharge, an electric field of a certain strength is required, yet the fields in clouds are not strong enough for breakdown. Scientists suggest that cosmic rays and cloud turbulence play a significant role in creating conditions for lightning. Lightning is not only an atmospheric phenomenon, but also an important indicator of processes within clouds. It helps meteorologists study turbulence and the movement of air masses. However, there is still no complete model that integrates lightning into meteorological calculations. Modern research on lightning. Today, scientists use unmanned aircraft to study lightning. These can penetrate thunderclouds where manned aircraft would be too dangerous. Research continues, and perhaps one day, we will unravel all the mysteries of lightning. Aircraft and thunderstorms. People on aircraft have repeatedly flown into thunderstorms, which poses a serious problem. As discussed earlier, an aircraft itself can initiate lightning because it is a large metal object. Of course, wooden aircraft would not experience such phenomena, but this is not a practical solution. Additionally, small aircraft, such as drones, may be too vulnerable, as they can easily be destroyed by strong electric discharges. Therefore, scientists are developing alternative methods for measuring electric fields in thunderclouds. One such method involves using large balloons, which minimize the presence of metal components and provide safer conditions for experiments. Radio waves and lightning research. Researchers are actively using radio waves to study lightning. As charges move within clouds, radio waves track their trajectories. By deploying multiple antennas, scientists can analyze signal delays and build three-dimensional maps of electric charge movements. These maps help researchers understand the complex processes occurring within thunderclouds. Sometimes, radio data aligns with what cameras near the Earth's surface record, while other times, they reveal unexpected movements that are yet to be interpreted. The challenge lies in the fact that optical systems cannot always be used in conditions of strong light scattering and poor weather. This leaves a vast field of study for young researchers. Lightning research is just beginning and represents one of the most fascinating and promising areas of physics. Friends, explore thunderstorms and lightning. They are yet another mystery of nature waiting to be solved. Subscribe to our channel and leave a comment sharing your thoughts. All the best, and until next time,